A few people are still joining, but they can rewatch the first minute of the session or so. A couple of housekeeping points that you might have noticed. On the Moodle page, a quiz which is still sort of hidden from you, at least you can't access it, has appeared under week 2. So you'll have your first quiz on Thursday in the lecture time slot next week. So just to talk briefly about what that quiz will contain, it's on slope fields. It's open book. You can use whatever resources you like, provided that you don't collude. You won't have time to collude because it's a 15-minute quiz. So the quiz opens, I think, at 12:30, and then it closes at 12:50. But that gives you a 5-minute window if there's any delays trying to connect to do the quiz. So you get 15 minutes or until 12:50. So if you try and connect at 12:49, you're only going to get 1 minute. You've got this 5-minute grace period at the start of the quiz for any connection issues. If there are connection disasters, take a photo of your screen with your phone and email it to me later. Then it's grounds for special con or a reset and something like that. We can deal with those because hopefully they're case-by-case basis. The quiz is on slope fields. I'm going to give you some pictures of slope fields, and I'm going to ask you to comment on the pictures. So you're going to have to briefly explain features of slope fields to me. I'll tell you what I want commented upon in the actual quiz, but that's kind of the thing that you should expect. I don't expect an essay. I want 1 or 2 sentences. That's even mentioned in the quiz, so don't write too much. Just write a brief response to the comment. Remember that a quiz is a formative assessment. The idea of formative assessment is you learn from it. It's okay to mess one up because they're such low stakes. They serve as a means of you checking how your education is progressing. If you understand something, then you should be good in a formative assessment, and a formative assessment should reflect your understanding. If you don't understand, then the formative assessment is telling you to go back and revise certain aspects. So hopefully that's all clear. Just quickly, any questions on the quiz before we start? If you're happy, click your happy face. To be clear, is there a requirement to? No, there's no requirement to upload anything. You should just be able to type in the Moodle box. So type 1 or 2 sentences in a short response thing. It kind of looks like our lecture survey. Turnaround for results. I think under the policy, I've got 2 weeks to turn them around. That's quite generous. It shouldn't take me very long to mark them. You'll get almost instant feedback because you'll type. You won't get it's not automatically marked, but once you've done the quiz, I think it shows you the correct answers. So you should have some feedback quite quickly, and then I've just got to spend some time in my life looking through all your answers and just giving a grade. But I don't think that'll take too long. I'm pretty sure you've got to have an assessment back by week 4 by the census date. I think that's the actual policy. All right. I'm going to kick off. I'm going to close my video and share my screen. So today we're going to talk about algebraic methods. Oh yes, I wanted to mention one more thing. In order to respond to a suggestion, someone made a suggestion in our course lecture box. I responded to it by not quite doing what was requested. People should be able to see my web browser now. There is now this tab on Moodle called Course Schedule, and you can click on it, and it will take you to a Google Doc, so a Google spreadsheet. This contains the week, the notional lectures, and relates the lectures to the regions of the lecture notes. So you should be able to quickly see, if you want to read ahead, where to read in the lecture notes. I've also got this little comments thing down the side. You'll note that we're actually very slightly ahead of where I thought we would be, because we didn't really talk too much about classifying ODEs yet. I decided to do things slightly differently. So hopefully that lets people check on the schedule of the course, and you can see what to study if you're interested in studying ahead. So today we're going to look at algebraic techniques for solving ODEs. Now, I did mention earlier that a solution of an ODE say you've got, I'll just write a first order ODE for convenience. Solution y of t makes this equation work. So if you're given a solution of an ODE, say you're given dy dt equals y, and you're told that y equals some constant times e to the t, you can check that this proposed solution is indeed a true solution of the ODE. Sub y equals a e to the t into the ODE. So your left-hand side, dy dt equals a, derivative of e with respect to t is just e to the t. And you note that the right-hand side is y, and that's just equal a e to the t. So left-hand side equals the right-hand side, which is exactly what's required for the equation. So if we put something else into this function, right, instead try y equals t plus b, for example. If we sub that in, dy dt equals 1, that's our left-hand side. Our right-hand side is t plus b, not equal. Therefore, therefore t plus b is not a solution. Okay, so that's what we mean when we say y is a solution of the equation. It satisfies the ODE. Everything works. It's happy. Sorry, I'm just checking where I am in my notes. Now, we've got a bit more terminology about solutions. We have general solutions, and we have particular solutions. A general solution involves a constant of integration. So we saw this idea with our slope fields. That we've got these this idea that we've got a family of different solutions. So we might have had a slope field that kind of looked a bit like this. So we've got this family of solutions that sort of come along and do that. It's a pretty weird looking solution, but it is what it is. So this red line is one particular. So these all of these different lines. That's our family of our general solution. And they're distinguished by a constant of integration. So if we say, well, we start here, that's going to identify our particular solution. And we noted that particular solutions, they're unique, distinguished by the initial condition. So you actually require an initial condition. You need an IVP, an initial value problem, to extract this particular solution. Okay. General solutions, particular solutions. So I'm going to give some examples now. E.g., let's say we had the ODE that I just looked at, dy dt equals y. The general solution is a constant times e to the t. Now you don't know how to solve this equation yet, but so just believe me, you know that that is a solution because you just saw me verify it. The thing that makes this a general solution is the presence of this constant of integration. For example, our particular solution to the very similar problem. Now I've got an IVP. The solution is e to the t. Note that a equals 1 if we're comparing to our general solution. So we've identified a very specific value of our constant of integration. Note that y of 0 equals e of 0 equals 1. So the solution also satisfies the initial condition.
Could you please repeat that?
So the solution satisfies the initial condition. If I take my solution, this thing here, and I plug in t equals 0, I get y naught equals 1. Okay, so I'll just pause for questions on sort of this idea of general and particular solutions. If everyone's happy, click your happy button. If you're not happy, click your unhappy button. And feel free to post questions in the chat or put your hand up or something. A is a constant of integration. So when you solve a DE, an ODE, you're actually integrating it in some way. You want to get rid of that derivative. I should classify that. Yeah, we can think of it as e to the power of c. I mean, we'll see how to solve these equations later. At the moment, it's just a constant, and it is related to the integration step. You'll see that in a couple of minutes. So the question is, where did we get e to the t? I haven't told you how to get e to the t yet. I've just shown you how to verify that it is indeed a solution.
So for particular solutions, are we saying that y equals e to the t, like that's the solution to the question?
That is the solution to the initial value problem. Initial value problems have both general solution. Well, an initial value problem only has a particular solution, but a particular solution will be a member of the general solutions to the ODE. So you've got to think of an initial value problem as having two components, the ODE and the initial condition. Because you can have solutions, members of the general solution, that do not satisfy the initial condition. So for example, if y equals 2e to the t, that satisfies the equation, right? You can actually plug this into the equation. It's just the case where a equals 2. But that will not satisfy the initial condition. So if you plug in t equals 0, you'll find that y is 2. So if you want to think about this in terms of a slope field or sketches of families of solutions, t, y, this is the exponential curve, e to the t, 2e to the t, etc. Right. So hopefully this shows you that this is the family of general solutions, and each one of these is a particular solution that's determined by the initial conditions. Yep, the particular solution is always contained within the general solution. In fact, how you solve these problems is you work out the general solution first, and then you work out this constant of integration. You'll note that you need one extra piece piece of information per constant of integration. I think that's the only thing that we need to note. Note 1 IC is needed per constant of integration. And you get every time you integrate to get rid of one derivative, you get a constant of integration. So the number of constants of integration you will get is related to the order of the DE. So if you've got a first order DE, you need one initial condition. If you've got a second order ODE, you'll need two initial conditions, and so on and so forth. Okay.
Hi, Duncan.
Yep.
Before you move on, why didn't the y equals t plus b work?
Because it's just not a solution.
So is that because when you derived it, you got 1 and you need dy dt to be y?
Yes. Yeah, that's
So-
exactly what the ODE tells you.
So the derivative needs to be the same as itself.
For that particular equation, yes.
Right. Okay.
If we have a more complicated example, let's think of this equal, say, y squared. An exponential isn't going to satisfy that. We don't actually know how to just guess a solution to this. This says that the derivative of y must somehow be equal to y squared. But let's say I've solved this equation and I tell you, okay, y equals this function. You can take that function and you can stick it into this DE and you can figure out how to solve it. Or you can figure out that the right-hand side equals the left-hand side and that it is indeed a solution. All right.
So then further down, that y of 0 equals 1, you introduce that further down as the initial value that it needs to satisfy as well.
Yes.
Okay.
So that lets you identify the constant of integration that you otherwise have.
And a was that constant?
Yes.
Okay. Okay, thank you.
All right, no worries. I'm going to move on now. I'll just put this in a box as an aside. I'm just going to skip chapter 2.4 for those of you following along in the notes. You can read it. It's called Solution by Inspection. It's a good thing to know because there are a lot of common ordinary differential equations, and you should learn to recognize the solution of some of those really common ones, in particular the exponential solutions. But at this stage of people's mathematical career, it's very difficult to learn to recognize things if you haven't seen how to solve them. So I think that it's a good thing to know about. It's a good thing to know that you can recognize some solutions, but I think that equations have to become, the ODEs have to become familiar to you first. So I'm going to move on over that. I'm going to talk now about 2.5, separation of variables. Separable equations have a very strict form. A separable first order ODE has the form. So when I say has the form, I mean can be written as. So you've got an ODE, you rearrange it, and eventually you can get it into this form. Can be rearranged to can be rearranged to, say, dy dt equal a function of y and some other function of t. Importantly, function of y alone So what's happened is that the DE has this magical form where the right-hand side is a product of two functions, one function of y and one function of t. Now, what that lets us do is it lets us rearrange the equation in a certain way. It lets us separate the equation. This can with all the y terms on the left and all the t terms on the right. Now, some people that have seen a bit of calculus in high school might be a bit grumpy about what I'm going to do next. I'm going to treat this derivative term as a fraction. Now, typically you're taught that this thing is unsplittable. You're not supposed to split this thing up. You're certainly not supposed to cancel bits out of it, and that's kind of true. The thing that I'm going to write down, it involves an informal step, and then I fix it, if you like. It's the informal step to me is like a mnemonic. It helps me remember how to solve these things. So I just treat this like a fraction, and I write dy on f of y equals g of t dt. This is strictly naughty, at least in the sense of I'm just rearranging these things as I would a fraction. What actually formalizes this is if you write in the definition of the derivative as a limit, then you rearrange that limiting expression. You can then integrate this expression, and it's formally correct again. Right? So you just have to, if you want, you can write this out as deltas. Can be So whilst I'm telling you that it's sort of naughty to think of them as fractions, you can formalize this by thinking about them as infinitesimally small objects in the limit as they vanish. And that's what we really mean by derivatives. What we have instead is dy. This is a legitimate integral. And that is also a legitimate integral. But because we have that, we can now go ahead and actually compute these integrals, if we know exactly what f and g happen to be, we can do this integral quite comfortably. And then we can deduce what y is, which is our ultimate goal. We're looking for y. However, for now, this is the solution of our ODE in integral form. And unfortunately, sometimes integral form is the best we've got. So I'm going to illustrate this with an example. And we're just going to see the same example we were just talking about. Y dt equals y. Oh, I forgot. Shit, I should have mentioned something else. Anyway, I'll come back to that. We're not going to specify an initial condition. We're just going to find the general solution at the moment. Doing our separation step, pretending that these things are fractions. Get dy on y equals dt. Now this is kind of naughty. We integrate, and now that's formally separated. This is how I generally prefer to do these questions. The naughty step, I don't write it, I just use that as a mnemonic, and then I put the integral signs on it. So now what I've got to do is I've got to compute these integrals. So this is a logarithm of the absolute value of y plus a constant of integration. This is the integral of 1, so that's t, plus some other constant of integration. Now, that's quite slow. Often, don't bother to write out 2 of these constants of integration, because you can see that we can just take a constant of integration, c2 minus c1. That's still a constant. We may as well not have bothered to write this out. I'll do this very formally this one time, so you can see what's happening. So d is still a constant. Okay, now what we want to do is we want to invert this function. We're still targeting y. We still want to know what y is. So to get rid of the logarithm, we can exponentiate. Okay, and we recall our log laws, which are our log and exponential laws, which let us write this. All right, so if you see a sum in an exponent, you can write that as a product of e to the t, e to the d in this case. I'm going to call that b. So we've got b e to the t, but that's still the absolute value of y. E to the d is still a constant. I want to get rid of these absolute values. So if the argument of the absolute value function is negative, that's like multiplying by -1. If the argument is positive, if y is positive in this case, that's like multiplying by +1. So what we can do is we can write y equals plus or minus, depending on the value of y, we're not quite sure when and where, e to the t. Right? The thing about plus and minus is that that's still a constant. It doesn't actually depend on y anymore, although you might think it does. It really doesn't. This thing is still going to turn out correctly depending on the initial condition. So you can write a e to the t. And so if you really want to follow back what a is in terms of the original constants of integration, you can back substitute all the way through, right? But it's really irrelevant. One thing that happens to constants all the time is they get abused. So everything that happens to a constant of integration, if you multiply by some other constant, you just change your constant of integration, right? So there's lots of these different tricks and tricks where your constant of integration will change, but because it's still a constant, you just write a different letter there. So that is the general solution to our problem. Not all of our problems, unfortunately. So if we were given an initial condition, we would be able to find a particular solution. Suppose y naught equals -1. Then, since y equals a e to the t, -1 equals a e to the 0. So I simply substitute in the initial conditions. And I substitute into the solution, into my general solution. Sub IC into the general solution. This implies, so e to the 0 is 1, a equals -1. And our particular solution is y equals -e to the t. All right, so that's how we can go ahead and solve these types of problem. And there's lots of different separable equations. So for example, you've got something like this. You can separate that to be okay, you integrate you exponentiate and muck around with the constants. And you get that as your general solution to the problem. All right, so I did that pretty quickly. Just before I pause for questions, I probably should have remarked upon what are called directly integrable equations. They're simpler than separable. Directly integrable equation has the following form. dy dt equals some function of t alone. If you've got a function of the independent variable, you can just integrate this thing. You can just integrate both sides. with respect to t. By the fundamental theorem of calculus, which says that integration is inverse differentiation, you have the general solution. So that's what we call a directly integrable equation. Now, why can't we just directly integrate separable equations? So back to our simple example. We found that is formally true. That's all correct, but useless. We do not know what y is, so we do not know how to compute the integral of y with respect to t. Okay, I'll pause there for some questions. If everyone's happy, click your happy face. If everyone's unhappy, click your unhappy face. If anyone's got any questions, shout out or type in the chat. Unfortunately, you don't necessarily get to solve every DE that you like. There's a hell of a lot of them that don't have analytic solutions. This is a great tragedy, but it's something we need to accept fairly early on. In first order ODEs, you know how to solve some separable equations. We need to know how to solve we know how to solve linear equations, and we know how to solve maybe a few nonlinear equations that admit integrating factors. Are higher order equations separable? Sometimes you can. I'm not aware of any examples off the top of my head. Things like du, a second derivative of u, for example, equals function of y, or function of u, function of t, say, that would still separate out. You'd still be able to solve it with these techniques. Separable can also mean additively separable in other contexts, so be aware of that. We won't treat higher order separable equations. I assume that there are obviously higher order separable equations that can be rewritten as first order equations that are separable. So in answer to that question, yes, we're not going to look at them, but not necessarily, right? The space of ODEs is bigger than separable and linear and trivially integrable, I guess. If anyone cares, there's a book by some Russian dude named Polyanin. That's usually in the library. It's about maybe 600 to 800 pages long. And this book contains most of the known solutions to ODEs. So if you're ever actually interested in an analytic solution to an ODE, that polyanon's a good reference. I assume that Wolfram Alpha knows them all as well. We'll be solving first-order linear equations. You don't necessarily know how to solve not separable and not linear. We won't talk about non-linear, non-separable in this course anyway.
Hey, Duncan.
Yo.
Integrating up earlier in your OneNote document, you had the integral of dy over y equals the integral of dt.
Yep.
What are you integrating those with respect to?
On the left-hand side, with respect to y, and on the right-hand side, with respect to t. That's a good point. I should clarify that. So in all of these separation steps, this integration is with respect to the variable as written, or the variable on that side. Now, if you're worried because you're actually apparently doing a different operation to both sides, you're really not, because these are dummy variables. You can rewrite them with whatever letter you please.
So you can integrate the left-hand side with respect to something and the right-hand side with respect to something completely different.
Yes. When I said this, right, naughty can be formalized, that includes formally writing down the integral step. So when you actually integrate this, you integrate it with respect to a dummy variable on both sides. And then for convenience, you write it down as the dependent variable on one side and the independent variable on the other.
Right. Screen there where you've
Yep.
written ex dot, and then you've written the question, the equation, and then an arrow. That line there. Oh no.
Sorry.
That's right. Further back up. Just you see that yellow where you set it off.
This one.
I think it's just off my screen now. It's at the very bottom of the screen.
Oh yes. Often ignored.
Yeah. So the bit of the blue line.
Yep.
So those integration, like what you're integrating with respect to there, you don't need those there.
Well, you do. You need to integrate the left-hand side with respect to y, and you need to integrate the right-hand side with respect to t. That's formally correct. It's just that the rearrangement to get to that is much more subtle than simply just moving, than rearranging the derivative like a fraction, and integrating both sides. I've omitted the formalism of separation.
Right, okay.
Because it's tedious. You're using the main result, which is the integral form. I'll just put a red box around it here.
Thanks, Duncan.
No worries. Sorry, I don't understand the question in the chat. We'll talk about that after the lecture. We're running out of time. So just quickly, I'll put a couple of examples. I'll write down a couple of integration examples for you guys to practice on. Okay, that looks good. They're all separable equations, except one. You should be able to solve all of them with the techniques that you've sort of learned in this lecture. Have a look at the videos online. I discuss a number of worked examples there. We've probably only seen one worked example thoroughly in this lecture. But yeah, other than that, if anyone's got any questions after the... Yes. So you should be able to find the general solution of them. They're just little practice examples that you can try. I can't find a particular solution. So Kadeja, yes, we have a lecture on Thursday, and the same day we have a quiz. You've got half a lecture. So at 12:30, I'll stop the lecture and say everyone should go do the quiz. It just means that everyone's in the same place at the same time. They're not like people don't get to know the questions beforehand. The quiz runs for 15 minutes from when you start or until 12:50. So if you the latest you can start and have 15 minutes to complete it is 12:35. You've got this 5-minute grace period to allow for any connection issues and things like that. And yes, it's on slope fields. If people who came in late are wondering about the quiz, it should be at the very start of this recording. It's the 23rd. Yeah, check Moodle. That's next Thursday, right? Yeah. And the link is on the week 2 page, or the week 2 tab. No, the lecture started bang on 11, bang on 12. Yes, the hour, it should be from the hour to 50 minutes.